Asymptotes are a key feature of any function that we're going to encounter at advanced higher level. What we need to know is, first off, we need to know what these are. So that's what we're going to talk about to begin with. And the second thing we then need to know is how to calculate them. Where do they exist on the graph, and how do we figure out at what point asymptotes exist? First thing we need to know though is, what is an asymptote? Well, quite simply, it's a point at which the function itself doesn't exist and it has no value. So the function will approach it from both sides, but it never touches, and it can be represented by a straight line. So if we think of the function f of x equal to tan x, we know that as we approach 90 degrees or pi over 2 in the tan function, the graph heads up towards infinity in the f of x direction, but it's never going to touch the 90 degrees. Reason being that we know that tan can be represented by sine of x over cos of x. And as we get to 90 degrees, cos of x is equal to cos 90, which is equal to 0. So we can't divide by 0, so we're going to get infinitely closer to it, but we're never going to touch that value. We're never going to have a value at tan 90. Plug in your calculator and you'll get an error message. We then know on the other side of the asymptote, we're going to do the same thing, but from the bottom. We're going to get infinitely lower in f of x and infinitely closer to the asymptote from that side, but again, it's never going to touch. So this here is a vertical line going through the pi by 2, where the function never exists, it has no value, it is an asymptote. Now what we have to be able to do is calculate these, but we also have to realise there's different types of asymptotes. We've got vertical types of asymptote, where we've got them existing at a point x and it's a straight vertical line up and down where the function cannot exist. So the function can't be calculated at this point vertically upwards. So that's what we were just talking about with the tan graph. There is another one which is called a horizontal or oblique asymptote. Now these are asymptotes that exist and take the form of a horizontal line through a set y value, or a straight line of the form y equals mx plus c. So it could be a straight horizontal line, similar to the vertical line, but for all the values of y at one set of points, or it could be a straight line in the form y equals mx plus c. So we're going to look at how we calculate each of those. Let's start by looking at vertical asymptotes. So if we imagine we've got a function, f of x, and it can be expressed in the format g of x over h of x. Now imagine both of these are polynomial function of degree 1 or greater, with the denominator h of x having a power higher than the g of x. We know at some point h of x is going to equal 0, which means that at some point we are going to be dividing by 0. So we've got a vertical asymptote which exists for that function. Think back to the tan one again. We had sine over cos, and at 90 degrees cos was equal to 0. We knew it approached the asymptote there. So if we take h of x equal to 0 and solve it, what we're then able to do is determine the values of x where these asymptotes exist. So we can determine which values of x give the asymptotes, so we know where they are on the graph. Let's imagine I've got a function f of x equals 1 over x squared minus 1. If we look at the bottom, with x squared minus 1, I know that at some point or points, x squared minus 1 is going to equal 0. At that point or points, at that pair of points if you like, what that means is the function is not going to exist, so we've got asymptotes that will exist. So what we're going to do is solve x squared minus 1 equals 0. Well, x squared minus 1 we know can be factorised, x minus 1 x plus 1, using a difference of two squares format. So from that, I know that x equals 1 and x equals negative 1. If you plug either of these two values in here, 1 over 1 squared minus 1 is 1 over 0. 1 over negative 1 squared minus 1 is 1 over 0 again, which means I cannot calculate either of these two values. So what that means is if I were to draw a sketch of the curve at 1 and negative 1, I'd have asymptotes of the curve where it wouldn't actually touch the curve itself. So it would get infinitely closer and closer and closer, but it would never physically touch the curve itself. The second type we said was horizontal or oblique asymptotes. So what we're going to do is we're going to imagine we take a function and we can now express it in this format. So f of x equal to m of x plus the g of x over h of x. Now, the g of x over h of x takes the same format as before. It's a polynomial over a polynomial where the highest power of g of x is less than that of h of x. What that means is then as x tends towards infinity, this fraction is going to tend towards 0. The bottom will always be bigger than the top, and as the size of the bottom increases, it dominates the fraction. The whole fraction will tend towards 0, but it will never actually touch 0. So we'll never actually get a value of 0 exactly. So what that means is we'll have this m of x plus values getting infinitely closer and closer and closer to 0. So what we'll be left with is this value plus a tiny wee bit, or this value minus a tiny wee bit, depending upon the signs. So we're going to get closer and closer to whatever the format of m of x is, but it's never going to touch it. So that means m of x is going to be a horizontal and or oblique asymptote. Now a key point to note about this one is we talked about the fact that the highest power of g has to be smaller than the highest power of h. So what that means is if the power on the top is equal to or bigger than the highest power on the bottom, we have to use the algebraic long division we discussed earlier on to split it up and get it into that format that we want. Once we've done that, we can simply read off the horizontal or oblique asymptotes. Now a key thing to note as well is a function can have a mixture of horizontal oblique asymptotes as well as vertical asymptotes. So it can have a combination of the two types of asymptote we've got. Let's look at an example for that one. So imagine I want to calculate the asymptotes of this function here, x plus 1 over x minus 1. Well, the highest power on the top is equivalent to the highest power on the bottom. So we want it to be in that format we had before. We've got m of x plus g of x over h of x. And we know that g of x has to have a power, highest power, that is less than that. So we've got to use algebraic long division in order to simplify that. So if we go back to the technique we had before, x minus 1 is dividing, so it's the divisor, and it's dividing the x plus 1. So we do x into x, that gives me 1. Multiply the x plus 1 minus 1 by it, and we put that on the bottom, and then we subtract it. So the x's disappear, I've then got 1, take away negative 1, so I end up getting 2. So what I can then do is express my f of x in the format of 1 plus 2 over x minus 1. So what that tells me is I'm going to get two asymptotes from that. If I focus on the fraction part here and look at the denominator of that, I know I'm going to get one asymptote when x minus 1 is equal to 0. So at the point x equal to 1, that's one asymptote I'm going to get that will exist. I'm also going to get one asymptote that will exist from the function in front of it. So I'm also going to get is another asymptote at y equal to 1. So again, if I were to sketch this graph, I'd have to make sure I marked on asymptotes. So one going up and down there at x equal to 1, and one going horizontally there at y equal to 1. So I get two different asymptotes that exist for that one function. As I said, you can have a combination. So don't fall into the trap of thinking there's only going to be one asymptote for every function. There may not be. You may get a couple. So we have to remember about these two types, and it's always the key thing. We always want it written in this sort of format here. You have to remember highest power on the top has to be less than the highest power on the bottom, and then you solve for the two types. Start with the vertical, look at the bottom first, then look at your horizontal or oblique asymptotes by looking at the part in front of it, your m of x. If you do that, you get all the asymptotes that you can have in the function, and it will then be able to be put together with everything we've done in order to be able to sketch the graph accurately and show all the key features of it.